Hi guys, in this video I'm going to give another CAVI example, and this example is taken also from the review by David Blay, and it's of a Bayesian Gaussian mixture model. Okay, so what is the process we are trying to model? So in order to generate an observation, we sample a cluster assignment, and then we draw from the corresponding Gaussian. So we have some prior over the different means of the clusters. And then there is some uniform probability. We have k clusters. The means are from k equal 1 all the way to big K. And the clusters for each observation, well, the I goes from 1 all the way to n, and also the xi goes from 1 all the way to n. Okay, so suppose we have some value and we have a cluster here, a cluster here, and a cluster here. So we randomly choose a cluster, and suppose we chose that cluster, and then we draw x from a random distribution centered at this location with a standard deviation of 1, and then maybe this is the point that we got. And then we sample another cluster, maybe this cluster, and then we draw from a Gaussian that is centered here, and then maybe this is the point we got, etc., until we get all the different points in our data set. And know that this is very similar to regular GMMs, but in a regular GMMs, we don't have this prior over here. We don't assume that the means, these locations are parameters. Yeah, we assume they are random variables. We assume some prior knowledge on them. Okay, so also note that CI is encoded as a 1-hot vector. So if we have, I don't know, 10, if big K is equal to 10, then CI will be a number between 1 and 10, but we encode that number, let's say 3, as 0, 0, 1, and all zeros afterwards. Okay, and also the sigma square here is some sort of a hyperparameter of the model. Okay, now what we want to find is we want to find a posterior cluster assignment. So the probability that the ith observation belongs to cluster 2, maybe, given that we know what is the data point. So if we know that this is the data point, what is the probability that it belongs to cluster 1, and what is the probability that it belongs to cluster 2, and what is the probability that it belongs to cluster 3. And also we want to know the posterior mixture component. Okay, so this is the probability of mu k of the location given all our data. So what we want to know for each data point which cluster it belongs to, and we also want to know what are the means of the clusters, where are the clusters located. So what we do this by maximizing the ELBO, of course, which is the log of the joint minus the log of the surrogate, and we do this using the Cavi algorithm. And the joint is just given by this, which is the process we described. We first draw k cluster centers, and then for each observation we choose randomly between one of the clusters, and then we draw a point from a Gaussian on that cluster. And since the cluster's centers are not correlated, this is equal to this thing over here. Okay, now we also assume that our surrogate can factor into each of our different variables. Yeah, we also assume what is poorly named mean field approximation. Q, the joint of all the vectors of mu and all the vectors of C, can be factored into these elements. Okay, now we can assert that the form of Q mu K is a normal, it's a Gaussian, and that the form of Q Ci is a categorical. But this will also rise naturally when we use the Cavi algorithm. Okay, so how do we maximize the ELBO? Well, assuming the mean field approximation, we can use the Cavi algorithm. And we saw in the previous videos that the Cavi algorithm has basically this formula where each component of the surrogate should be proportional to the exponent of this quantity, or that the log of this should be approximately up to a normalizing constant equal to this thing. Okay, and notice that here our z's are basically the mu1 until mu k and the c1 all the way to cn. Yeah, these are our z's in this case. And so the log of the joint, if we take this joint over here and we break it into a log, then by logarithm rules, it factors into these things. And now let's calculate this CAVI solution for the cluster assignment for the QJCJ. QJCJ, we can again say that it's categorical. It's, it gives you a discrete number between 1 and k. So it's a discrete number and it's final. So it has no other choice by being a categorical. Anyway, so, and remember that CJ is one hot vector. Let's see, if we take the log QJCJ and we say that it's approximately the expected value of this quantity with regards to anything that is not the J element, again, we can throw away everything that is not related to CJ, which is our variable of interest, right? Everything else will just be a normalizing constant. So here we have nothing that is related to CJ. We have one element here that is CJ. The rest, once we take their expected value, there will be some number, a constant to us. And here we will have something that is related to CJ. And here we will have one element, and here we will have one element, because these will be the jth element in both that we didn't take the expectation of. Okay, so this is what we are left with here. And notice that, well, we assumed that the prior on CJ is uniform. So we know what's the probability of CJ being this or CJ being this. It's just 1 over k. And so the log of this is just minus log of k, right? So it's a constant to us. We also don't need this. Okay, so all we are left is with this expression over here. Now we can write this probability as a product of each of the probability times Cjk, where Cjk is each element in this one hot vector. So in many of those, in k minus 1 times, it will be 0. And so this quantity to the power of 0 will be 1. And in one case, it will be 1, which will be the actual probability that we are looking for. So if we now take the expected value of this, we can break it down to this form, right? Because we take the log of this. And so it becomes a sum of the log of this. And then these exponents can go before the log. And then if we take the expected value is linear, so it goes into the sum. Okay, and so what is the log of P of xj given mu k? Well, we know that this thing is a normal distribution, right? Centered with mu k, and everything else is in the normal, is a normalizing constant. We don't care about it. So we can throw it away. And also the variance is 1. We assume that the variance here is 1. So we are left with this thing over here. And if we open this up, yeah, we will get xj to the power of 2, but we don't care about it. It's constant. It doesn't depend on ck. So once we will take it off of the exponent and then take the sum of it, it will just be equal to the sum over of cjk, which it will always be 1, right? Because there's only one in the one hot vector. So we don't care about it. But we are also left with xj time mu k time 2, and the minus and minus here cancel, and the half and the 2 cancel. So we are left with this times mu k, and then the expectation goes inside, and we don't care about the expectation with anything else except for the mu k, because all the other expectation are, well, not there. And also we will be left with mu k squared, and then we get the expectation of mu k squared. So we have here the first moment and the second moment of this distribution of mu k, right? Because this is the expected value with regards to qk, okay? The k element of the qk of mu k, right? So this is some distribution. We haven't found it yet, but we want its mean and its second moment. And so we can call the mean mk, and we can replace the second moment. Sorry, this should be a plus. So with the variance plus the mean squared. Okay, now, so what we got that by CAVI, that the q that Cj is equal to, let's say, the first element is proportional to this quantity over here, but this is a scalar value. So it's also true for each of the other vectors. And so remembering that also the sum of those quantities should be equal to 1, we get that the probability, yeah, for each of those events is actually a softmax, right? So we have this, and if we want to normalize it, we just have to divide this by the sum of this, and this is equal to the softmaxes, right? So we started from a uniform probability, right? For each jth observation, we had the same probability of being in each cluster, which was 1 over capital K. But after observing a data point, we moved to a non-uniform distribution. And note that this probability, yeah, this probability of QCJ depends on the mean and the variance, right? The mean and the variance of this QK mu K. So we have to find what that distribution is. So let's do this next. So the same as before, we take the log joint, and now we have to take, and now using CAVI, we are saying that the log of the mu jth element, yeah, of the QJ mu J is proportional to this quantity. And again, here we won't have anything that is related to mu K, so we don't care about it. The expected value of this will give some number, and we don't care about it. It's a normalizing constant for us. But we are left with the mu jth element here, and there will be some mu j element in this expression over here. Okay, so if we look at the mu jth element here, well, we said the prior that we gave it was a normal distribution with a mean 0 and variance sigma square. So this is proportional to this after we take off the normalizing constant, and this is the only expression that has mu j in it. And just as before, when we wrote this thing, if you remember, as this, then we can take the log of it, and we are left with this expression, right? As we did before. And now instead of having the sum over k, we can just, since we don't care about any component here that doesn't belong to mu j, we will just throw them away, and we will only be left with this expression over here that does belong to mu j. And the expected value of Cij, well, we saw that Ci distributes in the surrogate also categorical, and so its expected value is a probability. And so this is the probability of the ith observation being in the jth element, which is denoted by phi ij. And likewise here, we will get this expression over here up to a normalizing constant, which we throw. We can add these terms together and get these expression over here. And I threw the xi squared because it doesn't depend on mu j, and so it will just be constant for us for this distribution. So this is the form that we got. And again, this is a form of a normal distribution because the log of this is equal to this. So Q will be proportional to e to the power of this. And so the variance will be this thing 1 over this thing. And the mean will be this thing divided by the variance. Okay, so we have these two expressions, right? This is the variance of the mu j, and this is the mean of mu j according to our surrogate qj. And joining what we had before, we had this from looking at the c's, and note that q of mu depends on phi, and that q of c depends on mk and sk. So we again have this circular dependency here. Okay, so to compute sk and mk, you have to know the phis, and to compute the phis, you have to know mk and sk. And note that unlike the previous toy example, this dependence is not linear. So here we do need to do iteration from random start values until we find the optimum. Okay, and technically we are supposed to do this until the ELBO has converged or until the parameters haven't changed. So just for the fun of it, let's calculate the ELBO. The ELBO again is the expected value of the log joint minus the log surrogate. We saw that these are the log joint and this is the log surrogate. And if we take the expectation inside, we get this. Okay, so let's calculate each one by itself. So the log of the prior is just equal to this expression over here. And this thing is a normalizing constant. It doesn't change with regards to the parameters of the CAVI, right? The CAVI parameters are only these parameters. So if we change them, this quantity doesn't change. And so we can throw it. It doesn't track any changes to the ELBO that our algorithm does. Okay, so we are left with this. What about this quantity over here? Yeah, well, what's the probability of CI? We said it's just 1 over k. So the log of it is just minus log of k. And this is also a constant. Yeah, and we could have also looked at it like this if we would break it down to, yeah, so we could have taken the probability of CI to be the product of 1 over k to the power of CIK, the power over k equal 1 to big K. Okay, and then if we use the log of it, we get the same expression as before. Yeah, you can calculate it. But also intuitively, the probability of having each CI is just 1 over k, and so the log of it is minus log k, and then we have that this is a constant. It doesn't change with regard to the parameter of the Cavi algorithm. What about this expression? Well, this is how we wrote it before. This is again doesn't change with regards to the parameters. We develop this to this. And note that I use the fact that the C's and the mu's are uncorrelated. And so the expected value of their multiplication, right? Because we have CIK times mu k. So the expected value is just the expected value of one times the expected value of the other. And this is what I got. And again, here the xi squared, we don't care about them. They become constant with regards to the parameter. And this is what we are left with. Okay. And what about the surrogates? Well, let's develop the expected value of this term. It's just equal to this. If we open it up, we get this thing over here. And if we enter the expected value, we get it here. These all of these cancel, right? Because it's 1 minus 2 plus 1. We get this thing minus this thing. And well, here the sk cancel and we just get minus half. So this goes away. And for the final term here, we just get this thing over here, right? We just get that, again, we can write this down as product of phi ik over CIK on each k. And using the log, we get to this expression, and then taking the expectation, we get this expression. And then these are the whole terms, and we add them together, and we get the ELBO. Okay, let me switch into the code. And these are the packages I will use. I will use a hyperparameter for sigma, which is 3. And let's suppose we have 5 centers, 5 clusters. And let's say we have 1,000 observation. I randomly sample the means of the clusters. I randomly sample the clusters for each observation. And for each observation, I give it the relevant cluster. And this is the histogram of the different clusters that we had, and they are colored by their clusters. So here we have a lot of points, and here we have also a lot of points, here, here, here. And the histogram colors shows the cluster that each of the point belongs to. Okay, and now we use the Cavi algorithm. We start with random values for the parameters. So random values for the means, random values for the sigma square, and I just use the gamma distribution just because I want them to be positive. Random values for the phis, and I use Dirichlet distribution. So it guarantees that the sum of each row will be equal to 1. Okay, and here I compute the ELBO. This is I just entered the expressions that I developed before, and I give it a maximum iteration of 30. Okay, I also keep track of the elbows. And now here is where I do the Cavi algorithm. So first I do the updates for the fees. So I take the MKs and SKs to be constant, and then I update the fees. So I'm taking basically the previous versions of the MK and SK, and I update the fees. And then I do the same for the SK and MK. I take the fees to be the previous version of them, and then I use them to calculate the SK and MK, and these are the formulas that were colored blue in the notebook. And so here is the circular dependency. Here I use the MK and SK to calculate the fees, and here I use the fees to calculate the MK and the SK. And then I calculate the elbow. If the elbow doesn't change, if it's beneath some threshold, I stop. Okay, but it will go in maximum until 30 iterations. So let's do that. We can see that it's running. And this is how much the elbow is changing from each iteration. And we can see that after 18 iteration, it doesn't change so much, so it stops. This is the graph of the elbow. Okay, and now these are our final MKs that the Cavi algorithm took, and these are the true mu's. So you can see that they are really close. Yeah, so here we have 1.7, and here we have 1.7. Here we have minus 0.26, and here we have minus 0.24. We have 0.72, 0.72, minus 4.25, minus 4.23, 5.88, 5.81. So pretty close. And these are the variances for each point. We can see that there is very little doubt over the centers of each cluster. And now we can plot this. And this is how it looks. The vertical lines are where the Cavi algorithm says that the cluster center is. So pretty good, I would say. And notice that I colored them here manually because you can see that the first cluster that the MK gives is actually the second cluster. So this is why I want to paint it with the second color. And the second color is actually the fourth. And so I did this manually because, again, the Cavi algorithm, it gives you the clusters, but it doesn't guarantee to give you them in the right order. Okay, and I also added some code here to draw the two standard deviation, but they are so small that you don't see them really good. You just see the lines really, really close. So I rather not paint them. Okay, this was for a 1D data, but what if we had a 2D data? Well, here the only difference will be that the mu k will distribute bivariate normal with the center 0, 0 and sigma squared times an identity matrix. The CI will be just as before, categorical or multinomial. And yeah, also the XI will be multivariate normal with the mean mu k and the covariance matrix, which is the identity. Okay, so what will change from before? Well, before when we calculated the QJ/CJ, we arrived at this quantity, but now, instead of this quantity, we will have this quantity. Yeah, instead of this, we will have this because we're using multivariate normal. And it doesn't change a lot. It just becomes this quantity after we take away things that don't relate to mu k. Similarly, when we looked at QJ mu j, we reach this quantity. And now instead of this, we will have this quantity. Basically, the scalars become vectors, and a 1D Gaussian becomes multivariate Gaussian. And so we end up with this expression over here. And this means that mu j under the surrogate approximation distributes multivariate normal with the standard deviation of sk squared times the identity matrix, where sk squared is 1 over this thing. And the mean is this, only now xi is a vector, right? It's not a scalar value. So this is now the mean. Okay, and so the only thing left is to calculate this thing. And here we can use the property that the expected value of the dot product is just the trace of the covariance matrix plus the dot product of the mean. So the trace of the covariance matrix will be this, and the dot product of the mean will be this. So the formula changed as follows. The variance stayed the same. The mean also stayed the same, only now it uses vectors here. And the mean, well, kind of stayed the same, only now it has a dot product here. And now this is the update instead of what it was before. And if we want to code this, so let's do that I is a diagonal matrix. Mu is now sampled from a multivariate normal. Clusters assignments are as before. X is sampled from a multivariate normal. And these are now the data points in 2D dimensions. Okay, now we use the Cavi algorithm. We sample random start values for the MKs. We sample random start values for the SKs. We sample random phi's. This is how where the clusters are now, because were sampled at random around 0, 0. And now we do the same algorithm as before, minor adjustment for the new formulas that I showed you. Okay, it finished. And now these are the final MKs. These are the true MKs. And if we plot it now, you can see that each point is correctly, or seems to be quite close to the center of each cluster. So this is all for this example. I hope you enjoyed this video, and see you in the next one.